Imagine you're building a house. You pour the foundation, you put up the framing, you're making incredible progress. But every 10 seconds, you suddenly get total amnesia.
Oh, that sounds awful.
Right. You bulldoze everything you just built, you stare at a completely random pile of raw materials, and you try to rebuild from scratch just by guessing what you were literally just doing.
Which is completely insane.
Exactly. But if you're working in generative robotic control right now, that is effectively what your flow matching policies are doing. You are forcing your models to start from a cold, random blank slate every single time they generate an action chunk. Today on AI Paper Podcasts, our mission is to show you how a new paper called WarmPrior, straightening slow matching policies with temporal priors, basically cures this amnesia.
Yeah, and it's about time.
It really is. They replace that random start with a WarmPrior, which is a temporally grounded prior anchored on the robot's actual recent action history. So, instead of void, you start with context.
And this seemingly simple switch delivers, well, 3 massive compounding gains. First, geometrically, it straightens the probability paths the model has to learn, acting as an implicit optimal transport coupling.
Wow. Okay.
Yeah, it's huge. Second, temporally, it introduces this tunable knob for consistency, which directly prevents that notorious robotic failure mode we all hate, mode switching. And third, when you move to downstream applications, it massively shrinks the search space for prior space reinforcement learning.
Which means better success rates.
Exactly. You get a consistent improvement across the board, especially when you are operating at incredibly low inference budgets, like an NFE of 1.
A single network evaluation.
That's right.
I want to spend some time on that baseline, though, because to appreciate the fix, you really need to understand why the standard approach is just so broken.
It really is broken.
Yeah. Right now, flow matching and diffusion policies almost universally transport samples from a stateless standard Gaussian noise distribution. Mathematically, that's N0I. Why did the robotics community ever adopt this completely random starting point for continuous physical motion?
Well, it's just inherited baggage, honestly. We have to remember where diffusion models came from.
Computer vision, right.
Exactly, the vision domain. They were built for image generation, where the formulation was all about denoising from pure static noise. So when researchers brought these architectures over to robotics, which, sparked a massive revolution in imitation learning, they were hyper-focused on optimizing the network architectures themselves.
Right, like the diffusion policy backbone or those GR000T vision language action models.
Yeah, they optimized the ODE integrators, they tweaked the interpolants, all that stuff. But the prior space itself, it was just quietly left untouched. The field basically treated standard Gaussian noise as an immutable law of physics rather than, an actual design choice.
So we optimized the engine of the sports car, but we just kept using the same low-grade fuel we found in a lawnmower.
That is a brilliant way to put it, because an image of a cat is a static, independent thing. But robotic motion is a temporal sequence.
Right. A robot's arm doesn't just teleport across a table. Its position at millisecond 10 is physically tethered to its position at millisecond 9.
That's the crucial disconnect. The standard Gaussian prior is completely blind to time. And as our denoising schedules get shorter, because, we're trying to run these models faster for real-time control, the starting point has to absorb so much more of the burden.
Right. If you start from a stateless, uninformative void, your neural network has to do all the heavy lifting.
Exactly. It has to figure out not just where the arm should go next, but what the arm was even doing a fraction of a second ago.
So if starting from a random void is the core problem, what exactly are the authors replacing it with? I know the paper introduces 2 distinct flavors of this concept, WarmPrior Past and WarmPrior Preview. Let's start with the first one. How does the past version actually anchor the model?
It's a very intuitive intervention. So in robotic control, actions are typically generated in sequences called chunks. Let's call the length of a chunk H.
Okay.
WarmPrior Past simply takes the previously executed action chunk and centers the prior distribution's mean precisely on that past chunk. Then it adds a residual Gaussian perturbation just to give the model some flexibility.
Right. So your new starting point is the past action plus some noise.
Exactly, which we denote as sigma epsilon. And for this specific variant, they found that a noise scale sigma of 0.5 actually works best.
That makes total sense as a baseline. You're telling the model, look, start by assuming we're going to keep doing exactly what we just did and then adjust from there.
Yeah, it's a very safe assumption for continuous motion.
But you mentioned the second flavor, WP preview, is a bit more sophisticated. How does that one change the formula?
So instead of just looking backward, WP preview looks forward.
Yeah.
The model is trained to predict an action chunk that is twice the required length, so 2H. During inference, the robot only executes the first half, those first H steps. The second half is stored in memory as a preview forecast.
Oh, clever.
Right. And when the next decision step arrives, that stored forecast becomes the precise prior mean for the new chunk. And because a forecasted prediction is generally more accurate than just naively assuming the past will repeat itself, they can actually afford to use a larger noise scale here.
So they turn up the sigma.
Yeah, they set sigma to 1.0 to allow for more refinement.
Okay, wait, I have to pause you there.
Yeah.
Because when you explain it like that, it sounds fantastic at inference time when the robot is actually running.
It is.
But isn't there a massive chicken and egg problem during training? Like, if I'm training a fresh model, how do I use its own future prediction as an input before the model actually knows how to predict anything?
Yeah, that is the classic paradox in autoregressive training.
Yeah.
But the authors sidestep it using a very elegant proxy.
Oh, how so?
During the training phase, they don't use the model's flawed, untrained predictions. They simply use the ground truth target from the dataset as a stand-in for a perfectly calibrated preview.
Wait a minute, isn't that cheating? You are literally feeding the network the answer key as its starting point.
I know it sounds exactly like teacher forcing, but you have to think about the mathematical limit state of the model.
Okay, walk me through that.
At convergence, when the model is fully trained, its prior forecast of the current chunk should theoretically coincide with the actual chunk itself, right?
Right, if it's doing its job perfectly.
Exactly. So by setting the prior mean to the target action chunk during training, you are providing the exact distribution the model will eventually produce. The network's job is no longer to guess the target from nowhere.
Oh, I see. Its job is just to learn the residual correction.
Yes, the flow. It learns the flow between that WarmPrior and the final execution manifold. It completely eliminates the training bottleneck.
Okay, we have a proxy that works during training, but how does changing the starting point physically alter the neural network's job? Because the paper makes a really big claim that this, quote, straightens the flow. We need to explain what that actually means under the hood. Let's look at the probability paths.
Yeah, to visualize this, we have to understand what conditional flow matching is actually doing mathematically.
Right.
The neural network is performing an L2 regression on a transport direction. It is trying to learn the vector field that points from the source distribution A0 to the target distribution A1.
Makes sense.
But when you start from pure random noise, you create a severe endpoint ambiguity problem. Many completely distinct target actions, say moving the arm left versus moving it right, end up sharing the exact same intermediate points along the flow from that central noisy origin.
Right, because the network can't perfectly resolve which target it's supposed to hit from that murky intermediate state.
Exactly.
So it's forced to mathematically average over those ambiguous endpoints.
Yes, the network hedges its bets.
Mm.
And that averages things out, which curves the probability paths drastically.
I like to think about it like dropping a pin on a map for an Uber driver.
Well, that's a good one.
Right. Starting from standard Gaussian noise is like dropping a pin and telling the driver, hey, just find me somewhere in this massive city.
They'd be driving in circles.
Exactly. The driver's going all over the place, taking these highly curved, inefficient routes because they have to account for every possible destination you might be at. WarmPrior gives the model the exact cross-treat. It narrows the starting region so tightly that the route to the target basically becomes a straight line.
That is a perfect physical intuition for what optimal transport theory describes mathematically. WarmPrior basically acts as an amortized approximation to an optimal transport coupling.
But without the heavy computation.
Exactly. It avoids the massive computational nightmare of running a dedicated optimal transport solver during training. The authors actually prove this geometrically in the paper.
How do they show that?
They show that the branching cost, which is that irreducible error that forces those paths to curve in the first place, it reduces down to just 2 terms.
Okay.
It is the mean mismatch, which is basically your prediction error, plus the residual noise, represented as sigma squared times dW.
Let's unpack that last term for the listeners who might be driving or at the gym right now.
Yeah.
What is dW?
Right. So dW is the Wasserstein distance. You can think of it as the Earth mover's distance, the literal mathematical cost or amount of work required to move one distribution of mass to another.
Got it.
In this context, it represents the physical gap between your prior distribution and the true action distribution.
So if the branching cost is just the mean mismatch plus that Wasserstein noise term, that formula explains perfectly why the preview version outperforms the past version, doesn't it?
Exactly. Look at the difference in the mean mismatch. For WP preview, the mismatch is just the forecast error, how much the model's prediction was off.
But
But for WP past, the mismatch is the persistence residual, which is the actual physical difference between the last chunk and the current one.
And a dedicated forecast error is almost always going to be smaller than just a naive assumption that the robot isn't moving at all.
Exactly. Therefore, WP preview mathematically guarantees a lower branching cost.
And straighter paths mean the network spends way less of its capacity realigning samples from a random void and more capacity actually refining the precise microadjustments of the physical actions.
Which is exactly why this method shines at extremely low compute budgets.
Right, if your path is a straight line, you don't need 100 integration steps to follow it. The paper shows these huge success rate jumps at NFE equals 1.
Oh, massive jumps.
Yeah, on complex RoboMeg tasks like Square MH and Transport MH, they're getting huge performance boosts under a single network evaluation.
Because the baseline struggles to hit the broad side of a barn at NFE1.
Why is that?
Because it's trying to integrate a highly curved path in a single massive step. Mathematically, taking a single linear step on a highly curved manifold just shoots you off into empty space.
You just missed the target entirely.
Yeah, you produce a completely invalid action. But WarmPrior starts you so close to the manifold and the path is so straight that a single linear step actually lands you in a safe, valid action space.
But wait, if giving the model this cross street straightens the path so well, what happens if the target is actually moving?
That's the real test.
Right. Does locking onto a straight line make the robot too rigid to adapt? We really need to connect that sigma noise parameter to a real-world robotic behavioral issue here. I'm talking about temporal consistency and mode switching.
This is where the paper's 1D navigation toy experiment is just so revealing. Imagine a robot that has to navigate around a central obstacle to reach a goal.
Okay, pretty standard.
And the training data shows demonstrations of humans driving the robot both above the obstacle and below it. So those are two distinct modes. Standard flow matching models fail spectacularly here. They just oscillate wildly. They will start going above the obstacle, then jitter and try to go below it, then snap back above it.
Because they're independently picking a totally different mode at every single step.
Yes. Every single generation is an isolated roll of the dice, because a standard flow matching objective places absolutely no constraint, linking the chunk produced at step T to the chunk produced at step T plus 1.
It's the classic trap of independent sampling.
Exactly. But with WarmPrior, the sigma parameter isn't just arbitrary noise injected to satisfy some mathematical formula. It functions as a continuous, turnable knob between temporal consistency and multimodal expressiveness.
Oh, I see.
Because the prior mean is now correlated with the previous action, a small sigma keeps the distribution tightly clustered around the mode you're already in. The robot commits to going above the obstacle, and the narrow prior physically prevents the flow from crossing that vast empty space to get to the other mode.
But if the task requires high reactivity, say, the obstacle is a moving human hand, you can turn that knob up. You use a larger sigma to broaden the source distribution, which gives the policy enough spread to explore other branches and, say, suddenly dodge below the hand.
Exactly. You are explicitly giving the model permission to explore.
This raises an obvious question, though, for anyone listening who might want to implement this right away.
What's that?
If small noise forces consistency and stops the robot from oscillating, why not just turn the knob all the way down? Like, why not set sigma to absolute 0 and have a perfectly consistent deterministic policy?
The authors ran an ablation study on exactly that, actually, and the results are a stark warning against setting sigma to 0.
Really? What happens?
When you remove the noise entirely, you strip away the stochastic nature of the generative policy and turn it into a rigid deterministic regression model. You completely destroy the multimodality that you chose a diffusion or flow matching architecture for in the first place.
So it just averages all the human demonstrations into one useless, middle-of-the-road action that probably crashes straight into the obstacle.
Yes. And the failure is catastrophic, especially in WP past. If you set sigma to 0 there, the success rate collapses to around 5%.
Wow, 5%. Let's bring back the Uber analogy for a second. If you tell the driver the exact cross street, but you give them 0 flexibility to swerve around a pothole, meaning 0 noise, They just crash the car.
That is exactly what happens.
That is why the success rate drops to 5%. The prior mean in WT past is just an approximation. The network needs that residual Gaussian noise as slack to absorb the physical difference between where the robot was and where it actually needs to be next.
That is exactly what the noise is doing. It is the necessary slack that allows the network to correct a flawed prior. And the paper proves how powerful this temporal grounding is by doing something highly counterintuitive.
What do they do?
They completely disable explicit action chunking. They set the chunk length, h to 1.
Wait, no chunking at all, just predicting one single action step at a time.
Yes. On the transport MH task, when you force the baseline standard model to predict single steps, its success rate plummets to 1.3%. It completely falls apart.
1.3%.
But WarmPrior largely recovers the baseline performance even at h equals 1.
That's incredible.
It proves that the temporal grounding of the prior is doing all the heavy lifting for consistency. This is incredibly valuable for highly dynamic tasks requiring millisecond reactivity, where you simply cannot afford to be locked into executing an 8-step or 16-step chunk.
We've been talking entirely about behavior cloning, though, basically mimicking human data. But if you want to deploy this on a real factory floor, you usually need reinforcement learning to fine-tune it for novel situations.
Oh, absolutely.
How does WarmPrior hold up when you add RL? Let's talk about DSRL, or diffusion spatial reinforcement learning.
This is perhaps the most economically valuable insight in the paper for ML engineers working on actual deployment.
Okay, let's define what DSRL is doing first.
Right, so in standard DSRL, you freeze a pre-trained diffusion policy, and you train a separate RL agent to output actions in the prior space of that diffusion model. The RL agent basically figures out what starting noise vector will ultimately decode into a high-reward action.
But the standard prior space is N0I. Your RL agent is searching this vast, boundless, completely uninformative void, just hoping to stumble upon a noise vector that works.
Which takes massive compute and is highly unstable.
Exactly. But with WarmPrior, the RL agent no longer searches from scratch. The prior mean is already a temporally grounded, highly competent action sequence.
Right, so the RL agent only has to learn a tight, bounded residual correction around that mean. In the paper, they explicitly bound the RL search space to a range of -delta to delta, with delta equal to 0.5.
And how does that compare to the baseline?
For context, standard DSRL requires a delta of at least 1.5.
Wow, so you're giving the RL agent a massive head start. You're basically saying, look, don't bother learning how to move the robotic arm across the table. Just learn how to perfectly tweak the movement the arm is already executing.
The empirical results validate this theory perfectly, too. By shrinking and recentering the exploration space, the WarmPrior model stably surpassed a 95% success rate on the RoboMimic transport task.
95% on transport.
Yes. And to put that in perspective for the listeners, transport is the hardest task in that entire suite. Achieving a stable 95% success rate is a first for RL fine-tuning of a flow matching policy. It converged faster, and it reached a significantly higher asymptote than both of the DSRL baselines they tested against.
But they didn't just stay in simulation, did they? They brought this methodology to real physical robots.
They did.
Yeah, they deployed on a Franca Research 3 robotic arm using the GR000TN 1.5 VLA model. And this is where they stack WarmPrior against a very popular inference time technique called real-time chunking, or RTC.
Which raises an important architectural question, honestly. Since both WarmPrior and RTC rely on using the past action chunk to inform the next action chunk, are they just two different ways of doing the exact same thing?
They intervene at completely different stages of the pipeline, don't they?
Precisely. RTC works purely at inference time. While the robot is running, RPC literally clamps the early outputs of the newly generated chunk to match the actions that are currently being physically executed.
It forcefully suppresses those discontinuities.
Exactly. WarmPrior, on the other hand, works fundamentally at training time. It reshapes the actual source distribution so that the learned mathematical flow itself is straighter and more consistent from the jump.
So what happens when you stack them?
Yeah.
If I fix the flow during training and clamp the outputs during inference, do they conflict or do they compound?
They ran this on a highly dynamic towel folding task.
Well, that's a tough one.
Very tough. The baseline success rate was 50%. Using RTC alone brought it up to 67%.
Okay, nice jump.
Using WarmPrior alone brought up to 68%. But when you stack them, Using WP Preview during training and RTC during inference, the success rate jumps to 82%.
That is a massive delta for real-world towel folding. I mean, that's notoriously difficult because the fabric deforms constantly.
It proves definitively that these are distinct compounding mechanisms. You are fixing the curved, inefficient, learned flows on the training side, and you are acting as a safeguard suppressing interchunk discontinuities on the inference side. They just complement each other perfectly.
We really need to zoom out for a second as we wrap up this deep dive, because the implications of this go way beyond just getting a robotic arm to fold a towel slightly better.
Absolutely.
If this source distribution, this N0I prior, has been a completely neglected, inherited default in robotics for this long,
Right?
we have to look at the broader AI landscape. What other generative paradigms are currently suffering from this exact same amnesia?
It's a great question.
Think about video generation models like Sora or Runway. Think about sequential audio synthesis or continuous control in completely different domains like autonomous driving or fluid dynamics simulations. Are we blindly forcing all of these temporal models to start from a complete blank slate every single frame or every single time step?
Given the historical trajectory of diffusion models, it is highly likely that we are. The assumption that standard Gaussian noise is the optimal starting point for sequentially generated data is, honestly, a deep vulnerability in the current paradigm. What WarmPrior proves is that the prior distribution is not just some mathematical formality you copy-paste from an older paper.
Yep.
It is a first-class design axis that holds massive, massive untapped potential.
So the next time you are evaluating a generative model, whether it's a robot stuttering over a simple obstacle or a generated video flickering wildly between frames, ask yourself, is the model failing because the task is actually too hard? Or is it failing because we keep bulldozing its foundation and forcing it to rebuild the house from scratch? It might just be time to give these models a warm start.